Hello. Okay. Hi. Hello everyone. My name is Cheng-han. I'm from National Tsinghua University, and today I'm going to talk about my latest research on Class 0 circumbinary disk of VOA 1623A. So VOA 1623A is a very famous Class 0 covariant disk. It composed of three different protostars. One is A, and B, and W. A is actually a Class 0 source, and W is a Class 1 source. So this system is extremely young, and it's very important to study Class 0 covariant disk because first of all, it's difficult for simulations to create rotating disks around Class 0 sources. And also, the studying Class 0 disk also pinpoints the starting time for both planet and star formation. Previously, Nadia has identified the covariant rotating disk around the source A. And just recently, recently I will show you later, the source A is actually a binary. So my goal for the project is to determine the vertical structure of VOA 1623A, so a binary disk, and also understand the physical conditions around it. So the right side is actually, the color is actually the cycle 2 data from ALMA, and the white contours are actually cycle 0 data. You can see there are actually a lot of more structures around outside the white contours. So I'm going to use cycle 2 data to do my analysis. So, okay, so this is, you can see this is the new continuum. You can see that from the continuum data, the source A, the previously known circumstellar disk, is actually resolved into a circumbinary disk. There's actually two sources in the source A is actually a binary. So, so the color is C18O, 2-to-1 velocity map. You can see there's blue shifted on that side and red shifted on this side, so it's in the rotation. So my project is to try to fit the vertical scale height of the circumbinary disk of VOA 1623A. So I developed both the flat disk model and the flat disk model. So this is just a cartoon on the edge. You can see the flat disk is actually 3D, and the flat disk is just 2D. So in the flat disk case, there's in the z direction is actually I add a Gaussian, and there are two important parameters that I'm going to fit. The first one is the parameter A, that is corresponding to the density power law index. And the other one is H0, which corresponding to the scale height of the disk at 100 AU. So my method is first I use my model to generate some density, temperature, velocity data, and then I use red MC3D to do the radiated transfer and create synthetic images, and I write some header code to write some header, so I can input to CASA scene observe and CASA scene analyze to do the convolution. And in the end, I use CASA to create PV diagrams and compare with observation. So this one is my the flat disk model result. So you can actually see, it's a bit blurry in the projector screen. So actually you can see the blue line is the covariant rotate. Blue line is the info with conserved momentum, and the white line is actually the covariant rotation rotation velocity profile. So you can see the central star mass is fitted to around 0.2 solar mass, and you can see the whole disk is in covariant rotation. So for my flat disk model, I can actually start to feed the vertical scale height. So the A is the density power law index. So there's 2.0, 2.6, and 3.3, and the H0 is the vertical scale height at 100 AU. So if you look closely, for H equals 25, the central peak actually shifted. So there's an offset between the color, which is the data, and also the black contour. So from the and for H equals 10 and 5, I cannot really tell the difference. So I fitted the vertical scale height to be less than 10 AU. And as for the density power law A, I cannot really tell the difference. So the PV diagram is actually insensitive to the power law index A. And also, you can see here the disk, the data actually extended to 2 and 2.5 arcseconds, which is corresponding to 3,000 AU. So the question is, what exactly is the disk size of the circumbinary disk VOA 1623A? So this is just a close comparison between the two models. If you look closely, you can see that in the flare disk model, there's actually this component in here that actually corresponding to the data. So that's why I think the flare disk model is better than the flat disk model. And also, okay, the next part, I'm going to tell about how I try to constrain the size of the circumbinary disk of VOA 1623A. So first of all, I use the total power spectrum data to feed the foregrounds. So we feed so at velocity around 3.7, we can see that's the main component that's corresponding to the envelope around the circumbinary disk. So okay, and then we use the dendrograms to identify out the accretion flows. So the accretion flows are in the red boxes. So and you can see this is the blue shifted channel maps. If you look carefully, you can see that there's actually a gap. Okay, so there's actually a gap between the disk and the accretion flow. So we can actually use the blue shifted channels to constrain the disk size. As for the red shifted channels, you can see, okay, the disk in this case is really small, it's around here. So you can see the disk is actually connected to the accretion flow. So you cannot really separate between the disk and the accretion flows. So, okay, so I subtract out all the larger structures except the disk. So and then I create this PV plot. So you can see it's, the disk size around 180 AU. And also this part is also from the large scale structure. You can see this is subtracted out. So okay, so this is my conclusion. So we developed both flat and flat disk model, and we found the vertical scale height at R equals 100 AU is actually 10 AU. And also we constrained the disk size around to be 100 AU large. So actually we found that VOA 1623A circumbinary disk is actually very large and flat. So what caused this disk to be such large and flat disk, and what are the implications? So these will be the next steps in my research. So I will leave my conclusions here and take questions.
Any questions?
So I was just wondering that those two peaks might be artificial due to optical thick of the scenario.
You mean the two peaks might be artificial?
Yeah, because of optical thickness. Two optically thick at the center.
Too optically thick at the center. I think we need a higher resolution data to trace the dynamics to see whether or not is actually actually there might be binaries inside the continuum. So actually, if you okay, so basically from the PV diagram, I identify inside. This is in the inner region of the disk, around 0.5 r/second. You can see there's a very high velocity component. So it actually deviates from the Caparian rotation. So and also I look at the SO data. It shows the SO data shows that there's a accretion shock fronts on the northern part, but this is around the outside. So it is possible this high velocity component might be due to binary interactions in the inner disk that cause the motion to deviate. It deviates significantly from the Caparian rotation in the very inner part of the disk. So that's why we think the continued data might be actually correspond to a binary inside.
Just a quick comment. You mentioned about the size of the circumbinary disk. It's possible that the size of the circumbinary disk will increase with time because angular momentum is being transported from the binary into the circumbinary disk. So the size itself is not necessarily the size that had when it was formed, but actually it can expand during evolution. Okay.
Yeah.
Sorry, I was reminded it's really late. So you are welcome to talk to the student later. So thank you.
Okay, thank you.
So the final talk from the student Wang Jiawei from NTHU.